It on both now. I'm muted. I think I'm okay now, right? Great. Awesome. Thank you very much. Apologize for any additional things. So I did have one office, somebody stopped by my office hours on yesterday, and I just wanted to maybe go through. I didn't want to go through too much, but I did want to say maybe I didn't actually go through the office hours. Maybe I did it all via email. But I think for question 3, just so that we're all clear on things. So let's say that we had that we are having a sort of a 4-digit representation of, let's say, of pi. Or let's go ahead and, oh. I'm having one question. This is just from everybody, but let me go ahead and just quickly answer it. If you have proven in part B of C, if you've been proven in part, I believe in question, never mind, I'm going to keep just where I am right now. But the answer, sorry about that. So this is a 4-digit representation. I'll get back to your question in a second, just because I just started. So this is a 4-digit representation of pi, and maybe we have something like the floating point representation of 1/3 would be something like 3. Let's do something along the lines of 0.0031491. Okay, so this would be 0.003149. Okay. All right, so if I were to do these two values minus each other, right, with 4-digit accuracy, what I would do is I would say I would have 3.142 minus 0.003149. So what I would do is I would say that this is, well, what's actually occurring is that we have full accuracy during our operations, right? But then when we store, with our reduced accuracy, our 4-digit accuracy, or the 4-digit floating point representation. Okay, that's one thing I just wanted to make sense. So if I were to go ahead and do this, right, I would have, I hate doing simple math. And I acknowledge that it's a lost art of doing things quickly, but okay, so this would come out to being 3.138851, right? So if I was using rounding, which is what I've been using here, then this would be interpreted as 3.139. Okay. All right. So I just wanted to make sure that you understood. I think I may have forgotten to mention in our lesson of like how if you do this, or rather, if you're going to do subtraction with these 4-digit numbers, there's a higher or there's an accuracy during the actual floating point operations, right? Or during these operations, right? Plus minus multiplication division. But then when you actually store the number, you have the reduced accuracy. Okay. Makes sense? That's not really the lesson today. I think just to answer Kwang's question, for question 6, question 6 is our Taylor series question, I believe. So if you've shown previously what the accuracy or what the leading term, if you've shown, okay, just go ahead quickly. 60. You show the leading error term. Right? And then this is using Taylor series. And then in 6C, you state the actual order of the error. So it's just a check to make sure that everything's okay with understanding how we use order of error. Okay? Any other questions? All right. Hopefully that helps with everyone. Okay, let's get started. All right, so last lesson, let me stop writing in green because I'm going to go crazy. So lecture 6, we're going to start by talking about bisection method, which is what we sort of ended on last lesson. Okay, so what is the bisection method? It's a bracketing type root finding method. Main idea is that we constrain our domain around our root. Again, all these are for finding, all these problems that we're dealing with, right, are for given some function f of x, we're looking for f of x star. Or rather, we're looking for x star such that f of x star is equal to 0. Right, so when I say around the root, I'm really just saying around x star. Okay. What else? It's a linear convergence, a linearly convergent method. So I'm just going to say it has linear convergence. Okay. And even if it has linear convergence, it always converges, which is not always the case. and maybe I'll put a little star that I'll explain in a second. For this, right, yesterday we talked about sort of fixed point functions and root functions. This uses the root function. Of course, as soon as I write root function, I then write the fixed point function. What else can we say? We can also say that we have a few requirements, right, to use this method. First is that f is continuous, and that the interval AB must have one root. It has to have exactly one root, by the way. Okay, any questions so far? All right, and just a quick IBT aside, right? So the intermediate value theorem says that if f is continuous on AB, which, by the way, your book sometimes takes this statement and writes it as CAB. Okay. And let's say that there exists an S where f of A, or rather, let's say like this, that S is between f of A and f of B. Then there exists a C such that f, and by the way, there exists a C, and let me say that the C is between A and B. Such that our function f of C is equal to S. Okay. That's sort of a little bit of an aside, right, that I brought up at the end of class Tuesday. So for when you think about it in terms of our root, right, let's say applying to root finding, right, when we're looking for an f of x star equal to 0, then we can sort of modify this where we can apply the intermediate value theorem to say, hey, if we have a situation where either f of A is greater than 0 and f of B is less than 0, or if f of B sorry, if f of a is greater than 0, or sorry, less than 0, and f of b is greater than 0, and with the caveat that f is continuous, on AB, then there exists a P in A to B such that FP is equal to 0. And just to sort of make sure that we're on the same page, I switched from C to P, more so just to be in line with Asher Grief, so that we're in line with our textbook as well, right? So one thing that will be sort of like the crux of doing everything here, right? Well, let's unpack this, right? This is just saying that if we have a situation where, let's say we have a root somewhere, that if we have a situation where A and B go from positive to negative and such and so forth, or that oops, and vice versa, that there's going to be a root in between those 2 points, right? This is Calc 1 type stuff, but it's good to sort of remind ourselves. A convenient thing to sort of keep in mind throughout this, right, is that f of A in this situation and f of B, right, will be less than 0, right? It will be a negative number. Okay. Ooh. All right. This is only applying for this situation that we have here, right? In fact, this is going to be the main sort of driver for our bisection method. Okay. Any questions so far? I don't think I've done too new. So I'm going to introduce the pseudocode associated with our method, and then I'm going to I'm just gonna, how would I say? We'll do an in-class problem or a written problem, and then we'll do a computing problem associated with this, and then we'll talk a bit more about these properties of the bisection method. So for the bisection method, our pseudocode is as follows, okay? In my pseudocode, I'm going to describe my inputs. And what are the inputs that we have? Well, we're going to have A, B, F, and tall. So A is one endpoint, B is another endpoint. F is the function that we're importing or inputting. and tolerance is going to be an error tolerance. We're going to be outputting sort of an answer C, or rather P, which, by the way, this is equivalent to an iteration, right? So the actual code is very easy, right? We have while B minus A is greater than our tolerance, then we will have P be A plus B over 2. So this is essentially the midpoint. Then we're going to check if F of A times F of P is less than 0. If so, then P, or rather B, is equal to P. Otherwise, A is equal to P. So what this is doing is it's checking this note that I had before, and then using that as a criterion for bisecting the domain. And when I say domain, I really just mean the interval or the domain of interest, right? There's a common, there's a funny meme or just sort of Twitter joke that mathematicians are we always complicate all of our language all the time. And maybe it's a cultural thing, but I'm trying to be as clear as possible. So just make sure that I hold my feet to the fire is what I'm trying to say. All right, so keeping this in mind, this is going to repeat itself over and over until we get below our error tolerance. Okay? So what do we have? We have B minus A, which we can just think of the length of our domain, or the length of the interval. We have our midpoint. We have sort of our criterion. Right? And then we have sort of the bisection of the actual domain. So let's just do a problem visually, what would happen, right? With this, I kind of did one at the end of class, but it was a little bit rushed. So I'm going to just post right here, and I think that's enough space for it. Okay, so let's say I have our plot of the following type. I can tell I need to clean my iPad. So let's say that we have A right here. And let's say that B is right here. So if we were to just plot this, right, let's say that we have a function that looked like this over this interval. All right, this is just a generic function that I'm putting in. I got a little bit of a circle. Is everybody seeing okay? Just let me know in the chat if something's going funky. You don't want to tell everybody, you can send me a private message. Awesome. So what are we going to do? Let's go ahead and bisect our domain. So I'm going to say, okay, let's just take a midpoint through the center of our domain, right? So this would be our first P, right? What we then look at is, well, while we're here, right, we can see that this is positive, f of A is positive, and f of P is positive. So in our first round, we can see that f of A times f of P is greater than 0. So we now know that we're going to throw away pretty much everything on the other side, right? So we just don't care about this part of the domain. All right. And maybe that's a little bit too much white. Let's go ahead and just say that take advantage of this. No. Okay. Let me see if I can get a little lighter of that. Okay, there we go. That really, so maybe our better way to put it is that the region of interest then turns into this part of the domain. Okay. So then what you do is you treat this as your new A, and you take again another midpoint and see where that lands you. So again, we have a point where it's we have a point P that is positive, right? So we can again say that, or rather, we can also then say again that this is true, that the f times A times f of P, or f of A times f of P is greater than 0. So our new point of the domain of interest would be this area. Okay. Where this now turns into our A, and then again, onward we go. So here, just since this example is actually landing us nicely, we see that for our new midpoint, we can see that the point f of A times f of P will be less than 0. All right, so then we can say that B is equal to P, right? In the previous instances, we said that A was equal to P and A equal to P. All right, any questions? Oops. So let's maybe do an example to go along with all this. So we're going to compute the first 3 iterations of bisection method. To find the root of f of x equaling the square root of x minus 1.1 on the interval of 0 to 2. Okay. So one thing to sort of keep in mind, right, is you want to make sure that your conditions are all set, right, and we're all making sense. We need, what do we need? We need this fact, right? These two things are pretty essential for what we're doing. Okay, so we need that the product of f of a times f of b is negative, right, over here. But we also need that f is continuous. So we can look at this for a second. We know that the square root is going to be continuous for all non-negative values of x. So we're pretty good to go. And let's make sure with the other 2 items. So if we want to go ahead and plug in f at 0, we get negative 1.1. And f at 2, right, we'd get something along the lines of 0.3142, right? So we pass our check of making sure that f of a, or f of 0 and f of 2 are, in fact, less than 0. Okay. All right. Now let's actually get into the meat and potatoes of actually doing this. So like this is a, let's call this a check. Okay. Now let's actually get into our first iteration. So first things first, let's check. Let's say that p is equal to 0 plus 2 over 2, right? And so we know that p is going to be equal to 1. Let's evaluate f at p. So that's going to be square root of 1 minus 1.1, so negative 0.1. Beautiful. All right. So doing the check of, by the way, let's maybe state that a is equal to 0 and b is equal to 2 in this instance. So if I were then to do the check of f of p times f at a, you would have negative 1.1 times 0.1, negative 0.1, So that's going to be a positive value. So because of that, we then say that A is equal to P. All right. Any questions? I think there's a little bit of lag going on. I can't tell if it's my computer or if it's another computer. All right. I'm going to keep reading these were goods as okay. Well, actually, never mind. That's time stamped to way past where we are. All right. Let's just keep going. We'll do it in post. I'm joking. But let's keep going. So now we've set a new iteration. Right, where we have A is equal to 1, B is equal to 2. So P is going to be equal to 1 plus 2 over 2, so 1.5, right? So we got F of 1.5, right? Which is equal to 0.12474. Okay. So if we're doing F by P of P times F of A, right, then that's or 0.12474 times negative 0.1, which is less than 0. All right. So from this, we can then say that B is equal to P. So then you have our third iteration, where A is equal to 1, B is equal to 1.5. If we do another P, then it's 1 plus 1.5 over 2 equaling 1.25, right? And playing that in, this one, let's go ahead and let me just plug it into my calculator in front of me. Another way to say my computer. So we get 0.18, or rather 0.01803. One thing to note that is we're getting closer, right? And I mean that, what I mean by that, well, is that we're getting closer and closer to the root, right? So just going about with this one more time, we can say that this is F times P of F of A. I'm not going to do the math outright, but I know that F of A is negative, right? So this is, and F of P is positive. So this is going to be less than 0. Okay. So B is equal to P. All right, so let's not try to forget also our own like math knowledge here, right? If I wanted to figure out what the root was for this, right, I would say, all right, well, if I have f of x star is equal to the square root of x star minus 1.1 equaling 0, right? Then I can say that the square root of x star is equal to 1.1. So x is equal to 1.1 squared, right? Which is just shockingly very close to 1.2. Okay. Any questions? No questions, no concerns, no complaints. All right. So why don't we go ahead and set this up. So let me go ahead and share my other screen. All right, beautiful. Let me increase this to granny slash granny font size. Okay, great. So here, let's talk about what I've done here. All right, so what do I do? First thing I do in most occasions is I'm going to import NumPy. So one thing I will make a comment about, if people are importing math, the library math, as in import math, this is pretty outdated compared to what we're actually using for our method. There will be errors and will make your life more difficult if you keep using math throughout this course. So I'm just going to say it once, but let's just use NumPy and make sure that we're all on the same page. Okay? There's nothing special about math. Math was created way before NumPy. Okay? So I think I've already gone about how we define a function, but here I have a function where we have an input of an x, right? This is the value we're evaluating our function at. And then I'm returning a y, which is just the function value itself. So the square root of x, so mp dot square root of x minus 1.1. And I will post this I'll post this code online, right? Okay. So next thing I wanted to do is I wanted to sort of go ahead and delete this one. Is I wanted to also bring about sort of like looking at matplotlib. So matplotlib.pyplot, I import that as usually our plotting device for what we're doing. And I think that's generally a good idea. I mean, it's sort of the goal that we have. So what am I doing here? This should be similar to homework 0 that we just did, right? Where I have a grid. So I'm just plotting from 0 to 4 because I just want to see how it looks, right? So I plot the grid, I plot the function, I evaluate the function with the grid, and then this little grid line pretty much just what am I doing? Oh, okay, that makes sense. Sometimes you need to run it. So if I had run it just as I had previously, you could see that I just like having a grid to sort of help me interpret the graph a little bit more clearly. Right now, I kind of have an idea of where it hits our root. Okay. Other things that I've done are that I've included labels for the axis, just out of curiosity while we're here. Since oh yeah, it also takes into account LaTeX or Markdown syntax for some of this stuff, but for the most part, don't worry about that if you're just learning how to code. And you can do a lot of small different things, a lot of different things. So if I really wanted to look at the domain, right, I would maybe set xlim to be 1 and 2, and that would sort of spread that the plot that I'm plotting over the domain from 1 to 2, right? All right, so I think that we're pretty good on that, and this should have been already part of homework 0, right? So let's go ahead and define. Let's do a subroutine for our bisection method. So I'm just going to call this defining a bisect, and what we're going to do is, what are we going to input? We're going to input our endpoints, A and B. We're going to input our function, and we're going to input our tolerance. Okay? So the first thing that we should do is just pretty much just check if we have that F and P are that A and B are on opposite sides of our spectrum. So let's say that we have the following. Oh, that's not a statement. Let's say that what this would do is to say, we just want to print saying this is a wrong domain choice, right? Again. And this is me coding on the fly, so let's not take everything that I say. Let's be forgiving if something this. I have actual code written up for this. This is just more just seeing how I reasoned upon going with my with the code. So what am I going to do? First, I'm going to say P is equal to A plus B over 2. Okay. And just following the pseudocode that we already laid out, right? We can say while A minus B is less than our tolerance. Actually, let's put this inside, since we're not doing anything with it out there just yet. While A and B are greater than our tolerance, we set P equal to the midpoint, and then if F of A times F of P is less than 0, then B is equal to P. Else A is equal to P. Okay. So a few things to keep in mind. Python likes, Python cares about indentation. So if I'm entering and exiting a for loop, right, these things matter, right? But this should have been covered in homework 0. Okay. All right. So that's sort of it. As to get out of this while loop, I'm just going to return p in the long run. Okay. All right. So let's try with the function that we have. So let's say x is our root, and we're going to do bisect of 0 to 2, our function f1. Note that I called this function f1. Here I just labeled this function as, oh, thank you very much. Making sure that I'm not being dumb. Here I'm calling the function f fun. Okay. And lastly, in error tolerance, let's say 1e4 or 1e3. Okay, so, okay. I think I'm doing something too funny. Let's say that. It's angry that I'm assigning things beforehand, which is fine. I'll just define in that manner. Okay, so now if I want to print our value, this would be just 1. What am I doing wrong here? 1 sec, sorry. Well, a minus, oh, there we go. I see what happened. Okay. Apologize for looking at this code incorrectly. Okay, let's do like that. I kind of like that a little better. All right, so just make sure I had a bug. I had a minus b. You're allowed to fail. What you do is you then look at your code and see where things are. So I learned how to read these syntax errors. I knew that p wasn't being assigned right away, and so first I was like, okay, maybe this is just something weird with Python that I'm not assigning p. But then when I actually went to check my answer, it looked like something else was wrong. And there's not much code here to look at, but this is a pretty obvious one that, or this is a pretty common problem that comes up, right? If you make the wrong subtraction and whatnot. I guess my point being that don't be afraid if things go incorrectly, right? All right, so we can go, further and further with our digits, right? If we increase our tolerance, now we can note that we're getting more and more digits of accuracy, but we really haven't really discussed how many iterations we have. So let's say that we set n equal to 0, and then for every iteration, we just add 1 to n, right? And if I were to return 2 values, right, then let me do that in the following manner. Okay, so it took 28 iterations to get to our answer, which was which is accurate up to 10 to the negative 8 degrees. Are there any questions so far? So, I mean, I code in Python, C, MATLAB, um, Fortran, and things like that. There's gonna be some syntax error no matter where you go, unless you're always coding in the same language, right? So don't be afraid about these errors. It's more trying to figure out where possible issues could arise, right? So I wrote one that's a little. I wrote another bisection method um, that does a little bit better at sort of looking at things. So I wanted to see what was happening just in terms of actual storage. So I'm showing you this code more so of how maybe I would structure something. So if I'm, and let me call these P's instead of C, or work with me now that I was using C as the variable, but I chose P as the value. Okay, so if I wanted to see what the iterations were doing in time, I would store those values and then output them, right? And that's pretty much how that pretty much is what I've been doing here. The only complicated thing that's just a little bit nuanced is I initialize P as being sort of the number of zeros and like the max number of iterations that we can take, even though we know how many max iterations. And then I sort of make a smaller. I store it in a smaller with a smaller footprint of an array later. So what this does is it pretty much says you're not using all your entries. Let's just use the ones that we used in the previous one. So if we actually go ahead and print these out, right? Not that it matters. I'm using P or C. We can see that how close we're getting based off of our answers, right? So I can sort of tell you so this is just a way of seeing what the code is actually doing, right? These first three are the values that we chose in our first iteration. Or actually, I think maybe the one thing that I should add to that is, oh yeah, we were using between 1 and 3. So let's do 1 and 2. There we go. That makes more sense. All right. Any questions? All right, beautiful. No questions. Joking. Please ask something. I'll wait a minute for people to sort of collect their thoughts while I set up on my iPad.
I had a quick question.
Yeah.
This is a bit of an aside, but so this method wouldn't work for, say, like if your function was like x squared because it's positive on both sides, it wouldn't be able to
That's a perfect
process
question.
that.
That's a great question. It would not be able to work on that level.
Okay.
You have to rely on the fact that there's a change of sign, right?
Right.
Also, x squared, right? We like one of the things to one of the things to also keep in mind, sort of like in the first round of things, was I think in the lecture 5 when I went over like root finding methods, like one of the challenges is whether there isn't a root or if there is a point, right? Or if they're multiple, or if it's two sides of the function. What I'm trying to say is there are conditions for root finding problems in general, right? The idea of it being having a root on both of x squared. Sorry if that isn't making any sense. I'm just blathering right now. I would say that let's not worry that your question is a good question. And it's something that we consider all the time. And just started to figure out what this. By the way, last thing before we go, just to sort of look at what's happening, right? You can see the root get closer and closer. Let me go ahead and turn on the grid. All right, so I'm plotting both the zeros and sort of our grid. If I just wanted to go ahead and just set the x limits, I would just say let's look at 1.1 and 1.25. And you can see how it gets closer and closer to the root. I think maybe I need to put some brackets on there. Okay, great. All right, let's keep going with this. I know some of you apparently took it in engineering analysis too. That's great. I don't know if you guys talked about convergence rates. So let's go back to talking about on the iPad. So let me go ahead and share. All right, so here we are again, right? So a few things to sort of keep in mind with our bisection method. So the first, let's go ahead and look at this. So one thing that we can always say, right? Like I said before, it will always converge. With the one caveat that unless we accidentally arrive at a point where FP is equal to 0, right? But it's sort of like a blessing in disguise, right? Because that's our sort of goal. All right, so in essence, what you do is you sort of add a little snippet of code that says if f of p is equal to 0, and by the way, you need to use those double equal signs if you've not coded before. This is a logical statement or a logical expression. It says it's true or false, right? Well, it looks at whether this is true or false, rather. And then what you do if that is true, then you just put a break, right, in our while loop. Okay. That's sort of maybe a little minor point. But another thing that we can sort of think about, right, is how we can sort of ask ourselves, how close are we to the root? Maybe I'll use a little different color. And let's ask ourselves generally, how close are we at any given iteration? Okay. So let's say that we start, and we're just going to look at the number line for now, just because that's really what's important here. If we think of our interval a to b, right, the farthest and our endpoint would be or sorry, the farthest our arrow would be initially, right, would be here, right? It would be in this sort of in the center of what we're talking about. So we could say that it's at most going to be or b minus a over 2, right? It's at most going to be the halfway point. Or at least that half length. If you have a big question, could you... Okay, I got one question. Of course, everybody can see. I don't know if this is a relevant question or not, or if it makes sense, but is this sort of analysis similar to what a graphing calculator goes through when you use the zero feature? Yes. I believe it's either that or Newton's method, but I think because of the robustness of bisection method, it is in fact this is what's used for your graphing calculator. So that's a great question. Thank you. Sorry if I sort of stop myself here or not. Also, feel free to talk. Feel free to interrupt me, right? I'm here as a human. I'm not here as a pre-recorded text. All right. All right. So this is also true. The same thing is true if we think about the distance that A and B are. If we think of the distance from B from our root, at most, it's going to be B minus A over 2, right? So if we were to take a midpoint, right? Oops. Right? If this was to be our P, right, then the farthest it would be half the length, right? It could be either there or there, depending on how which side is the interval that we keep for the bisection method. So, by the way, if I'm talking about P, really, we can think of this as being sort of some sort of iteration, right? Because it is. We can say that xn is equal to some P from the nth iteration. Okay. So keeping this in mind, right, then if I were to ask what's the distance, the max possible distance that x star is from x1, which is the first iteration that we have, well, it's going to be half of the original of what was the previous length, right? So it's going to be b over 2 times 1/2, right? Now let's say that our interval of interest, right, is here, right? So then we take another p in the center. Then let's say our root was right there. Then we would say that at most it's going to be about half as well, or half of the previous interval length. So I'm going to convert to using, I'm just going to say 2 to the negative 2. Okay. And you keep going with this, right? the farthest possible distance, right, is always going to be for each iteration. Right? So what's happening here? It's saying, okay, x star minus x to the n is equal to b minus a over 2 for 2 to the negative n. Okay, so we can think of this as being sort of our error bound. Right? Furthermore, we can also set a tolerance, right? Or we can set a tolerance of how close we want to get to x star, right? And with that, we can use these two facts to determine the number of iterations we take. Okay. So let's go ahead and do that. If I were to go ahead and take this value up here, first, and let's say that I wanted it to be less than our tolerance. Then I could divide by the tolerance on both sides. And what else? I could also divide by 2 to the negative n. Why am I dividing by 2 to the negative n? Well, the goal here, right, is that we really want to find what this n is. So we need to solve for n, right? N is corresponding to the number of iterations, right? So that's why we're doing what we're doing. And apologies if that division looks funny. Let's rewrite our equation now. So we have b minus a over 2 times the tolerance is to be less than or equal to 2 to the n, since we divided. Let's go ahead and take a log of base 2. And we find that our log of base 2 is, the log base 2 of b minus a over 2 times the tolerance has to be less than, pretty much that we need an n to be greater than this value over here, right? Okay. So just to do a quick calculation, right? on the number of terms that we would need. All right, so let's say that I was wanting an iteration, or I just wanted to calculate the number of iterations that we needed for something. So let's say I set a tolerance equal to 10 to the negative 10. Just a quick question: how far? What is the smallest tolerance that makes even some amount of sense in our code here? Just a quick little question for anybody who's paying attention. What's the closest? There we go, machine epsilon, right? You don't want to get less than 10 to the negative 16, because that doesn't make, at that point, you can't fit really, actually. You can't, there's too much accumulated error. Anyway, let's keep going. But I just wanted to make sure these things are on the back burners. Anyway, so we have tolerance of 10 to the negative 10. I'm going to set that my A is equal to 0 and B is equal to 2. Do we need any other information? No, we don't really need any other information. So let's go ahead. So we have log 2 of B minus A over 2 times tolerance. So log 2 of 2 over 2 times 10 to the negative 10. So we're left with log 2 of 10 to the 10, which is equal to 33.2. So from that, we can say that we need n equal 34 iterations. Okay. One major comment that I'll make is that this is an issue that it's very slow, right? In the sense that 34 iterations is a lot. The other comment that I'll make is it's kind of cool to sort of think about a method that works regardless of your function. But that's sort of the benefit and the flaw. So last thing I'm going to do before I'll let you guys go is talk about the convergence rate, and then we'll start on fixed point functions on Tuesday. All right, so let's sort of designate our error. I'm going to write error as ERR at the nth iteration as being pretty much bounded by B minus A over 2 by 2 to the negative n, right? Again, this is kind of like x star minus xn, right? So most times when we're in this world, we only deal with error bounds for the most part as a way of making sure that we're conservative in our estimates, right? So if we have let rho be our convergence rate, then this convergence rate is going to come from sort of the error at the n plus 1th iteration over the error of the nth, right? From this, we're assuming that we have a linear, which makes sense. If we go ahead and do that, then we have b minus a over 2 times 2 to the negative n plus 1 over b minus a over 2 times 2 to the negative n. Bada bing, bada boom. Get some cancellations. And all that we're left with is 2 to the negative 1. So we have a convergence rate that's 1/2. Okay. So again, slow, but we'll get us to the root every single time. So next lesson, we're going to talk about fixed point functions. And we have versions of fixed point functions that take advantage of our derivative, or rather of properties of f, right? Whereas in these sections, we've really not done much. We've only talked about the domain. All right, any questions? There's homework 1 due today. Let me know if you need office hours or anything like that. And I'm happy to help. All right. If not, I will end the meeting to end this sound.